In this example, we're going to look at how to determine the electric field due to a long line of charge. So our picture looks something like, we have a very long line of charge, something like a wire, something like that. And we'll have this in the y direction. Our x direction will then come out this way. And we're going to determine the electric field at some point P along the x-axis away from the line of charge. Now this line of charge extends from L over 2 to negative L over 2, making the whole length of the charge length L. Now we'll divide this wire into small little segments, and we'll start with examining what the electric field is at point P due to just one of these segments. Say this one right here. So this segment is a distance y sub I in the y direction. It is the distance r sub I away from point P and makes an angle of theta sub I with respect to the x-axis. The electric field at this point, if we're going to assume that this line of charge is all positive, will point in this direction. So this electric field vector is then going to be E sub I. And again, the angle is also theta sub I. Now this line of charge has a charge per unit length of lambda. And again, that's defined as the charge on the entire rod divided by the length of the rod. So Q is again the total charge on the rod or the wire, and L is total length of the rod. Now in this particular example, it's uniformly charged, meaning that each one of these little segments that I've drawn has the exact same amount of charge as every other little segment. So we know that our electric field is equal to the force that a positive test charge Q would experience at that location. So if we are looking at just one little segment, we can assume that that little segment acts like a point charge. Then we can use Coulomb's law to figure out the magnitude of the electric field. So Coulomb's law will tell us the force, and again, that is K Q1 Q2 over R squared. This is Coulomb's law. We'll plug that into here and rewrite as so. So we have our test charge, then plugging in Coulomb's law. I'll rewrite this a little bit in a basic sort of way. My Q2 is actually the test charge that I have there, so that's why that's written as a lowercase. And again, the distance between the test charge and the source charge is R. So I can cancel out my test charge, and I end up with this. I'll go ahead and drop the subscript now that I only have one charge to talk about. We can also rewrite this using the permittivity of free space constant, plugging in for K, getting this. So this is the general equation that we're looking at. But we have a bunch of little pieces, and we're going to need to figure out what the electric field is in strength and direction for each of those little pieces. So if we focus on the electric field, the magnitude of the electric field due to the ith piece, so that E sub I that I'm talking about there, I'm going to end up using the permittivity of free space constant instead of K at this point. So the electric field due to the ith piece is going to be whatever tiny charge is on that little piece over the distance from that ith piece to point P. So again, if we look at, I'm focusing on this one little segment here. This one little segment has some fraction of the charge, and I've already shown the distance there. So let's go ahead and focus on what's going on in the x direction. So what I have here is the total electric field for the ith piece. Now I want only what's going on in the x direction. So we'll write sub x there, so I know that I'm only focusing on what's going on in that x direction. So, using my triangles, and I've got one right here, if this is e sub I x, then this part is e sub I y. I can use trigonometry to figure out that the x part is e sub I times the cosine of theta I. We just calculated what e sub I is above, so I can go ahead and plug that in. The next thing that I've got going on is that I've got multiple variables here, and they really all kind of depend on each other. This theta I is going to depend on exactly how long r of I is, so I can find a relationship between those two. So if I look for the relationship between those two, again, I'm focusing just on what a basic triangle is, so we're looking at trigonometry here. I know that the distance, which is the hypotenuse of my triangle there, is going to be equal to the height of that little piece that I'm interested in, yi squared, plus the distance of point P away from the line of charge, which I'm going to call D here, and I'll go ahead and mark on my diagram as well. All of that square root. I can also use trigonometry to find out that cosine of theta I is going to be equal to the adjacent part of my triangle over the hypotenuse. The adjacent part of my triangle is D. My hypotenuse here of this distance triangle is r sub I. Now if I plug in for r sub I that I just figured out, I can rewrite this as cosine theta I is equal to D over y sub I squared plus d squared quantity square root. So since my point P is not moving, D is basically a constant. Y sub I is just the distance from the x-axis to whatever segment you're looking at. So I'm going to take my cosine theta I equation here and my r sub I equation here and plug them in for my e to the ix equation. So that means the only variable I'm going to end up with is going to be y sub I. Alright, plugging in for r sub I squared, so I get yi squared plus d squared. My square root goes away because the bottom part of this fraction was ri squared. And then plug in for what I have for cosine theta I there. I get this. This one happens to be under the square root with a d on top. So let's simplify this a little bit because it's kind of a mess. I notice that I have similar denominators, they're just at different powers, so I can make some simplifications there. So if I combine this, that's going to take it to the 3/2 power. Now, if I want to figure out what the total electric field is in the x direction, I need to sum over all of those little tiny segments that I was looking at. The total electric field in the x direction, E sub x, is going to be, again, the sum from I equals 1 up to however many of these little pieces I have of E sub I in the x direction. So we can plug in for E sub I in the x direction. My constant can come out. Now, what we really want to do is have these little segments be as small as possible. So if they're as small as possible, then we're going to have basically an infinite number of them if we're making them infinitely small. So that will eventually replace our sum with an integral. But before we can do that, we need to take this delta Q that we've got and express it in a slightly different way. the way we'll go about doing this is by utilizing the fact that our charge density on our line of charge is equal to the charge over L, which is something I gave you in the beginning. So because this is uniform, if I'm looking at just one tiny piece, then the tiny charge on that tiny piece is equal to the length of that tiny piece. So I can rewrite this so that my tiny charge on my tiny piece is equal to lambda times the length of that tiny piece. I can also rewrite what my lambda is here. Since lambda is just the constant, the ratio of the charge to the length for the entire thing, I can rewrite this as Q over L times delta Y. So, we'll take this new expression for delta Q and plug it into our equation of E sub x. So I can pull the Q divided by L from right here, outside of my sum. Right now we still have a sum, again, from I equals 1 up all the way up to n. D, again, is the distance from the line of charge to the point P. Delta Y is how long that little segment is. And the denominator stays the same from what we had before. So, again, we've got D, which is just how far away point P is. And our other variable Y is the distance from the x-axis to whichever segment we're interested in. So the point of doing this is that if we have some function, say I'm graphing the electric field as a function of Y. So imagine this is something totally different, some random distribution. At this point Y, I have an electric field that's that much. If I move over a little bit, it's a little bit stronger. For some reason, if I move further, it goes lower. And so there's some distribution here. Each one of these little segments has a width of delta Y. Now, if I were to sum over all these segments, I'd find out what the total amount of the total strength of the electric field is. So if I were to write this down, the total electric field is then going to be the sum of the electric field at each one of those points times the width. So basically what we're looking at is, if we imagine that in this graph I've got right here, I've got a bunch of little rectangles. I'm basically looking at what is the area of each one of these little rectangles that I have here. If I make this delta Y smaller, I'll redraw a quick one that's a little bit smaller. So imagine I'm able to make these little delta Y things even smaller than before. Something like that. You get the idea. I'm starting to get a more smooth distribution here on my graph. It's not quite as jumpy. So the smaller we make this delta Y, the closer we get to approximating something that looks like an actual smooth function. Again, these are all E on the x-axis, Y, or E on the y-axis, on the vertical axis, Y on the horizontal axis. So the smaller I'm able to make these little delta Y segments, the more continuous my function gets. So basically what we're doing is we're turning our total E equals to the sum into an integral of a function with respect to Y times dy, which is the derivative of Y there. So basically what we're doing mathematically is we're calculating the area under a curve, which can also be expressed as a sum of little tiny pieces there. So this may sound familiar from your previous calculus classes, it may not, but I wanted to get at the specifics of what we're actually doing here. So, in order to get the most, in order to evaluate our total electric field. We're going to assume that each one of these little pieces, these little segments that we've been talking about, is infinitely small. So we're going to be able to turn our sum into an integral. So again, our sum, I'll rewrite just so that we're all on the same page here. Our sum, when we're talking about segments of length delta y, looks like this. Now, if we make those segments of delta y infinitely small, then we can evaluate this as an integral. So it looks like we're just changing a few symbols. Hopefully we're all on the same page as to what this actually means mathematically and physically, what we're physically doing here. So my d here is the distance, and dy is now that infinitely tiny segment that we're looking at. Everything else here will remain the same. Now we need to know what to evaluate this integral over. Since our variable here is dy, that's a unit of length. So basically we need to know, well, how long is this wire? Well, we know in the positive y direction it stops at L over 2. In the negative x direction, or negative y direction, it stops at negative L over 2. So that's what we want to evaluate our integral over. Now, this is a standard integral that hopefully you have learned in calculus already. If not, look it up when you're going through and doing these types of problems. So I'm not going to go through the mathematics of evaluating the integral. We'll just move on to what the integral ends up becoming. So when you evaluate the integral, you get y. Let's step back. This integral, when evaluated, turns into this. Then we need to plug it in it's a definite integral, so we'll have to actually plug in our full range of lengths, which is what we'll go through and do next. But when you evaluate that integral, it ends up becoming y over d times the square root of y squared plus d squared. So now evaluating this from L over 2 to negative L over 2. Every time you see a y, we'll plug in L over 2. And then minus, every time you see a y, plug in negative L over 2. Since any negative quantity squared ends up becoming positive, I have not put the negative inside the parentheses here for L over 2 in the denominator. Simplifying this a bit, I can see that my L outside of the brackets cancels with the two L's inside there. And again, it has to be both because this is not multiplication, this is subtraction. So you need to do it from both. And I can go ahead and take into account that if you subtract a negative number, you're really just adding between the two. The denominators of these things are the same, so I basically have 1/2 of this huge quantity plus another half of this huge quantity. Basically means I just have one of that big quantity. So rewriting this, that gets me this. So there's an expression for the total electric field only in the x direction. So what about the y direction? Now, if you go back and take a look at the picture, you'll notice that it's symmetric over the x, which means that anything that's happening in the y is going to be happening in the opposite direction. So if I do a quick redraw of this, I won't include all the little parts, but hopefully enough for you to get the idea. If this is point P here, then this segment of length Ri has an electric field that points this way, that we'll call E sub I. And this segment which is the same distance away, just in the negative direction, has an electric field that's symmetric over the x-axis, meaning the magnitude of the electric field in the x direction is the same, but in the y direction it's equal and opposite. So that means that every vector that points this way in the electric field is going to cancel the y component of it that points this way. So you'll end up with nothing in the x direction, and your E net will only be in the x direction here. So this is all about symmetry, which is going to be something that's going to help you a lot. So basically what this is telling us is that the total electric field in the y direction is 0. Because every single segment is going to have another segment in the negative y direction that's going to cancel out that y component of the electric field. Now we can only say this because it is exactly the same length in positive y as it is in negative y. If it weren't symmetric, then there would have to be a little bit extra that we'd have to account for. But because it is, then we can say that the electric field due to this rod is basically just equal to whatever the x component is, since there is no y component. So rewriting what we calculated for the x direction, and because we always talk about our, since we're only talking about magnitude here, we're going to do absolute value of Q, just to make it a little more general. In this example, we said it was positive, but the strength of this this electric field would be the same regardless of its negative or positively charged. Now, if you go through and take a look at the example in the book, it's going to assume that this rod is of infinite length. So one of the things that we can go through and do is some sanity checks to make sure that we're on the right track. So we'll go through a few sanity checks. So if D happened to be much, much bigger than L, meaning that we are very far away from this rod compared to how long it is, then our denominator here, D squared plus L over 2 squared, quantity square root, if this is much bigger than this, then that's basically going to end up approximating just D. Then our electric field due to this rod would simplify to this. So 1 over 4 epsilon naught times the charge over the distance squared. And the reason it's distance squared is because there was still a D outside of the square root. We only simplified the square root down to D. Now, if anyone's noticing, this is the electric field due to a point charge. What we started with in the beginning, if we were looking at just one segment. So what this means is that if the distance away from the rod of charge is so big, to you it's basically going to look like just a point. So if you're looking at this really long wire, and if you're standing really, really far away from it, that wire is basically going to look like a point. So now let's imagine that you're so close to this wire you can't see the ends. So this would be the case if L were much, much bigger than D. So the length of this thing is so long that if you're standing right up next to it, you can't see the ends whatsoever. Whereas the previous example is you're so far away, the ends look like they're the same place and it's just a point. So this L, much, much greater than D example is what the book derived. So this is why, so far, my solution is slightly different from the book's. So in this example, we basically need to take a limit as L goes to infinity of what we've already calculated. So as L gets closer and closer to infinity, that means this part right here is going to end up mattering it's going to be so much larger than d squared that it's going to overtake that radical there. So in that limit, we'll still have q on top, but it's going to be over d, this is the d outside of the radical, times L over 2. So if our length is so long, that's going to be the dominating factor. This little tiny d squared inside of the radical isn't going to matter, so then square root of L over 2 quantity squared is just L over 2. So let's go ahead and simplify some stuff out here. We can rewrite things a little bit. I'll bring my 2 up top. I can see that that cancels one of the 2's down there. And I can see that this right here is actually just my lambda, my charge per unit length. So rewriting one last time, I get 1 over 2 pi epsilon naught times lambda over d, which is exactly what is shown in your book. So, sanity check, everything looks good. So I've now basically gone through and shown you how to derive or determine the electric field due to a long line of charge, regardless of its length. We've got an infinitely long charge, we've got a definite length charge. So you should be able to use this example in future problems to see the steps of going through and working things out.